Hello, welcome to Mat-073. My name is Rob Reynolds, and today we're start Chapter 8. Our very first section talks about graphing exponential functions. We're also going to be looking at the inverse function for exponents, which is logarithmic functions, and we'll look at a couple word problems that are applicable to exponents. And then maybe how to solve for exponents would be the inverse, which is logarithmic functions. So first of all, we want to look at some rules for just graphing exponential functions. And exponential functions have a point, they have an asymptote, and then they either have growth or decay. So if we can get those three things down, then we can look at graphing all exponential functions in this standard form. Y equals a to the x. So y equals, if I say 2 to the x, some books call this a, some books call this a b. I'm going to call this b for the base. So if I were to put it into this standard graphing form, it would actually be 1 times 2 to the x minus 0 plus 0. So be careful because it looks like the value of a is 2, but actually if you write it in this form, the value of a is 1. So that's a start value, and it doesn't look like I'm moving it left or right or up or down, horizontally or vertical. No horizontal vertical shifts. The asymptote is always y equals d, and in this case d is 0, so here's a horizontal asymptote. And then we use our rules for growth or decay. If the value of a is less than 0, then that would cause decay. If x is negative, that causes decay. Or if the b value is between 0 and 1, meaning a fraction, then it's decay. And there's no decaying factors for this particular example here. So it would have growth. And you read a line like you read a book from left to right. So from left to right, this function is growing. There's additional points on here. And if you want to find those, you can just type those into your calculator. So basically, there are 4 different types of graphs. This one, it looks like it starts at 2, but the actual value of a is 1, so you start at 1, asymptote at 0, and this has growth. This one is actually written y is equal to negative 1 times 2 to the x. So this starts down here, but still has an asymptote at y equals 0 because there is no vertical shift. And because I have a negative a value, that's one of the decaying factors, it's going to come down this direction. So again, from left to right, it's going to decay. A third scenario would be a negative x. So again, the value of a is 1, so I'm starting up here. Still have a horizontal asymptote at y equals 0 because there's no d shift. But this negative x right here is going to cause decay. So it's going to start up high and head down low. And then if we have 2 decaying factors, that would cause growth again. So here I've got a negative a value. If I were to write this again, y is equal to negative 1 times 2 to the negative x minus 0 plus 0. I've got 2 decaying factors. I've got a negative 1 and a negative x. So that's going to cause growth, but I still start at negative 1. Asymptote is still at y equals 0. And then I have growth. So here are the 4 different basic shapes. Either I can start at positive 1, like these 2 graphs, and have growth or decay, or I can start at negative 1 and either have decay or growth. So let's take a look at our first example. I'm going to start here at negative 3. I'm going to put an open dot there because I'm going to move this 2 units to the right. Always go the opposite direction when you see these parentheses. And 1 unit up. So 2 right, 1 up. There's my point. Remember, all exponential functions have a point. And I start at 0a. Find that point. I need to get my asymptote, which is always y equals d. In this case, d is negative 1. Or excuse me, positive 1. So I have an asymptote here. And then I look for any of the decaying factors, and I do have a negative a term, and 1 decaying factor causes decay. If I would have had 2 decaying factors, I would have growth, but since x is positive, That's not decay, and the B value is not between. So I only have one decaying factor, so that causes decay. Let's try another example. This time the start value, I'm going to put an open dot at 0.3. I'm going to shove this open dot 2 units to the left. I'm going to go the opposite direction here. And then I actually, oops, don't put a point there though. 2 left and then 5 down is the 1 point that I'm looking for. So 2 left, 1, 2, 3, 4, 5. So the C value, the horizontal shift, always goes the opposite direction, and then the D shift goes the direction that you think it should. So this D either is the vertical shift, and then the C is the horizontal shift, which goes the opposite direction. Because when you set that factor equal to 0, it'll go the opposite direction. So then I look for either growth or, oh, let's get the asymptote in here. The asymptote's at -5, so -2, 1, 2, 3, 4, 5. And then I talk about growth or decay, and it doesn't look like there's any decay. Oh, there is a decaying factor. The decaying factor is right here. So I have a B value between 0 and 1. So that's going to cause decay as well. So I'll start up high and head down low. Again, if you want a more accurate graph, you could just plug this into your calculator and find a quick T-chart, which I'll show you that strategy as well. But I think the purpose that I'd like for you to know is just generally speaking, what does this exponential function look like? And I'm going to start at, oops, -1. Put an open dot there. This is 2 minus x. When I set that equal to 0, I get -x equals -2. So x equals 2, which is positive. So that's going to move to the right. And then this says 3 units up. So 2 right, 1, 2, 3 up. The asymptote is at y equals 3. That came from my D term. That's always the asymptote. And then I look for growth or decay. And I think I've got 2 decaying factors. I have a B value, but I also have an A value that's less. Uh-oh. And I've got a -x. In fact, I've got all 3 decaying factors. So that means it's going to be decay. So I would start up high and head down low. Again, don't cross that horizontal asymptote. That's the definition of an asymptote. What the function approaches but never crosses. There are exceptions to that, but that's the general rule. So this one, I'm going to start at -1. I'm not going to move left or right, but I'm going to go 1 unit up. The asymptote is at y equals D, which is a 1. And I have 1 decaying factor. So that's the -A term. So that would come down. This one, be careful. It looks like 1/5, but there's actually a 1 out front. So that's the start value. Move this 3 units to the left. Asymptote is at 0. And I've got 1 decaying factor, so that would be decay. Here are some other examples. You're welcome to try to graph these. I'm just going to slide through for sake of time. If you would like to pause the video and try to graph these before the answers, that would be great. Here's the answer for number 6. Here's number 7. Again, I would try to set this equal to 0 to find out the C shift. So this is 3x equals 6. So this is actually 2 units to the right. This says 4 units down. This is tricky because, again, if you set this equal to 0, it actually goes 3 units to the right because it's positive. Similarly, this goes 2 units to the right, 3 units down. Here's the way the book explains it, is just to plug in a T-chart, which I'm not a big fan of because, of course, your calculator, if you just hit second graph, if you go to your y equals and type in 3 caret up x, and then just hit second graph, you'll get an instant table set up. Then you could just plot these points. Looks like 0, 1 is a nice point. 2, 9. Kind of takes all the thinking out of it, if you ask me. But you can see they're still following the rules. Y is equal to 1 times 3 to the x minus 0 plus 0. So I'm still starting at 0, 1. The asymptote's still at 0, and then there's no decaying factor, so you have some growth. Again, if you wanted to find some extra points, you could do a quick t-chart. This one I can see is going to have some decay, but again, if you would like to do a t-chart and just plug in points and go brain dead, that's certainly a strategy. So notice that if there's no horizontal shift or vertical shift, if it's in this form, y equals, here's your a term. See, this is calling it a. I would call that a b term, because I would have written this y is equal to 1 times 1/3 to the x. So be careful. This definition of a is different than my definition of a, which I was doing a times b to the x. So I use b for the base. But if it's in this form, y is equal to some number to the x, then it's always going through 0, 1. So this one is a horizontal shift, so it's not going to go through 0, 1. This is going to actually move 1 unit to the right. Again, because when x minus 1 equals 0, then x equals 1, and that moves to the right. So you can see this yellow dot moved it 1 unit to the right. This is going to go 2 units down. So instead of starting right here, it moved it down. So the inverse of an exponent, exponential function, is a logarithmic. And that literally means, inverse means every time you see an x, write a y, and every time you see a y, we're just going to replace it with an x. So instead of 0, 1 being a point on the exponent, then 1, 0 is a point on the log function. So the purpose of the log function is to help us solve or undo exponents. It's kind of like addition and subtraction undo each other, and multiplication and division undo each other. So here's a inverse function. Instead of y equals 3 to the x, where we would look at the graph of this going through the point 0, 1 and having a horizontal asymptote at y equals 0, the inverse of horizontal asymptote is a vertical asymptote at x equals 0, and the inverse of 0, 1 would be 1, 0, and this has growth, this function has growth, and because there's no decaying factors, and this function also has growth, so it would look something like this, which is the inverse of the exponent. So they didn't write the word logarithmic function, which we'll study later, but that's actually what it's happening. So why do we need logarithmic functions? Because they help us solve for time or some kind of variable or exponents. And so we're going to introduce a general formula here so you can see some application, and compound interest is probably the most important formula for dealing with logarithmic or exponential functions. So P stands for the initial amount of money. It stands for the principal amount of money. So this is the start value. Just like the formula that we had, y is equal to A was my start value before. So now it's a P. This is the B value, the base, to the NT. N is how it's being compounded. And if N is being compounded annually, which this first example is, then N would just be 1. But our later examples, I'll be showing you how we could change N to 4, 12, 52, 365, and there are others depending on which words you use here. Semi-annually is twice a year. So let's try annually first. Let's use this formula. So the initial amount of money is $60,000. So I'll say A is equal to $60,000. 1 plus the rate is 5%. I'll write that as 0.05. And the part A just says find a function for the amount accumulated after t years. So I'm done with part A. Part B says let's let the time be 6 and go find the amount. So I'll just take 60,000 and multiply by 1.05 to the 6th and get about 80,000. And then the last part says actually graph the function, which is what we've been spending this whole time on. And so here's the author, and then you can see the graph of the function is the start value is 60,000. We've got nice growth. There's no decaying factors, and we have a asymptote at y equals 0. So if you want to just continue this function, you could, but you can actually just, again, just plot some points on this. So if we change this word annually to compounded n times a year, then we have to use either one of these numbers. So I'll give you an example here. If it's compounded quarterly, that means n is 4. So I basically do the same thing. Suppose there's $2,000 invested, so that's the principal, at a 7% rate, so it's 1 plus 0.07 divided by n. We just talked about that being compounded quarterly, so I'll put a 4 here for the word quarterly, raised to the 4 times 3.5 years. So be careful how to type this in. Sometimes students forget to put parentheses around this. Some students would prefer just to simplify this first, but don't round more than one time. So if this turns out to be a long stringy decimal, then I would not encourage it. But this is nice, 3.5 times 4, I think it's 14. So you could type that in. But I would really kind of get used to typing this in with these red parentheses. I'll show you here once. I like to only hit the enter key once, and I like to type the whole equation in. So 1 plus 0.07 divided by 4. And here's where I need, well, my calculator, I don't need parentheses because when I hit caret up, it actually keeps it up there. But if your calculator doesn't do that, then you'll have to put this 4 times 3.5 in parentheses. Just play around with your calculator and make sure that you're getting the correct answers. I'm getting 25.49, and then round to the nearest penny is 83 cents. And this is also what the author got here. If you have any questions, feel free to email me.